So in this question, we're asked to solve for the transfer function g, which is equal to the angle theta 2. So that's the angle of this part of the shaft here. And it's divided by t, which is the applied torque. And we can see from the diagram it's applied onto this other part of the shaft. So to start off this question, what we're going to want to do is draw one free body diagram for every degree of freedom that we have. And the minimum number of degrees of freedom is going to be how many inertias that you have. The only exception to the rule when they're not going to be equal is sometimes you might end up with components in series without the inertia in between, in which case you would need to put in another angle, so like theta 3 or whatever, to measure in there and draw an extra free body diagram of what's going on in that section of the shaft. But looking at this, we don't have any components in series which aren't already being measured, so we don't need to worry about that. So what I'll start with is drawing the free body diagram of the first mass, or inertia. Alright, so separating this component out, so we have a applied torque onto this component, and we can see it's drawn clockwise. And we're going to have some resistance due to this inertia being attached to a damper and a spring. So if we look at the damper first, so the damper is going to try and resist the direction of motion. So if the torque is applied this way, so clockwise, I'd also expect the shaft to spin clockwise. So let me put that in. That's my inertia term, the constant multiplied by the angular acceleration. So what I would expect is this damper is going to try and oppose the direction of motion. So it's going to go backwards, and the size of it is going to be the constant multiplied by the angular velocity of this part of the shaft. So since it's butted up against a wall, it's basically just going to be how fast this part is rotating, which is theta 1 dot. So the other part that I need to include is from the spring. Again, if my inertia is going clockwise, I would expect my component, the spring, to resist that motion and try and bring it back to where it was. And the size of it is going to be the constant k multiplied by the angular displacement of my shaft through this component. So because it's between two different inertias here, we need to take the difference between them. So it's going to be equal to whatever theta 1 is minus whatever theta 2 is, the difference between their angles. Alright, so that's the complete free body diagram. Let's just repeat this for the second one, and then we'll go through and develop the equations of motion. So taking out this component here and going through the same process. So I'm going to assume that if this torque is applied clockwise and this one's spinning clockwise, this one's probably going to spin the same way as well. So we'll start by marking that in. So this is the size of the inertia multiplied by the angular acceleration. This one's theta 2 measured here. And then we need to put in the spring and the damper's effect. So let's start with the damper again. It's going to try and resist the motion, so it's going to go backwards. And since it's butted up against a wall, we're just going to take the damper and multiply it by the velocity of this, which is theta 2 dot. Obviously butted up against the wall, so we don't need to take the difference. So now we can put in the spring. So again, it's going to try and resist the motion, and it's going to be equal to theta 2, the one we're looking at relative to J2, theta 2, minus the other one, theta 1. So as long as you always follow this pattern, for the ones where you need to take the difference, it's going to be the angle on the component that you're looking at, so J2 in this case, minus the one it's attached to, which was theta 1. Alright, so let's go through and develop our equations of motion. So the equation that we need to satisfy for the rotational systems is that the sum of the torques applied to our shaft have to be equal to J multiplied by theta double dot. So for the left hand side here, it's going to relate to all the lines that I've drawn in solid, and the right hand side is going to be the ones that are dotted in. That's the inertia term. So I'm going to say that this is the positive direction for the sake of this calculation. It doesn't really matter which one you pick as long as you're consistent. So we're going to have the torque T applied in the positive direction. We've got the damper part applied in the negative direction. And we've got this applied in the negative direction as well. And on the other side of the equation, this relates to this, and it's in the positive direction, so it's going to be J1 theta 1 double dot. Alright, so I may as well at this point try and get this in a form that's going to make it easy to solve. It's going to turn into simultaneous equations between the one we get here and the one we get for the other side. So for that, I'm going to leave the t on one side of the equation and move everything else to the other, because everything else has theta terms in it. So let me just do that. And I might also expand this while we're here. Alright, the next thing I'm going to want to do is Laplace transform it. And what I'm going to do is assume that all initial conditions are 0. So initial velocity and positions are at 0. Okay. So that means when I Laplace transform it, if things have dots, they're just going to get the equivalent number of s's. So t is a function of time, so when we transform it, it just basically becomes itself. I would capitalize it, except I already used a capital, so all good. J is a constant, it's not changing with time, and theta is. It's got 2 dots, so that means when we Laplace transform it, it gets 2 s's, and again, you would capitalize this variable, but you know, it's kind of hard to capitalize theta. Next we have d, and I think I've dropped the, that should be d1. And it is a constant with time, so it just stays the same, and this needs to be transformed. It becomes s theta 1. K is a constant. This has no time derivatives on it, so it's just going to stay the same. And same with the one on the end. So the last step that I'm going to do here, just to make it easier to solve, is I'm going to factorize. So everything with a theta 1, we've got J1s squared, D1s, and K. And then everything with theta 2, all we've got is K. And notice the signs on these. I'll come back to it in a moment. But yeah, this has worked out, everything in this bracket is positive, and this has worked out to everything is negative. So let's go through and repeat this process on the other one. Alright, so we've got this torque here applied in the negative direction, so it's minus d2 theta 2 dot. This is also in the negative direction, and the other side of the equation relates to this part here. It's drawn in the positive direction. Alright, so let's go ahead and shift everything to one side of the equation again. The intention here is to have everything with thetas in it on one side and everything else on the other, but we don't actually have anything else, so it's just going to be 0 left on the left-hand side. And I'll move everything else. And at the same time, I'll expand again. Alright, so now we can go ahead and Laplace transform. So 0 is just going to remain 0. The first term is going to become J2s squared theta 2. The next one gets 1s, and the others remain the same. Alright, and we're going to go ahead and factorize it again. So I'm going to take out theta 1 first, okay, and this is the only one with theta 1. And then theta 2, we've got all this stuff. Oh, I've dropped the 2 again. Here we go. Okay, and what we can notice is that we've got a negative on the theta 1s now this time, and positives for all the theta 2 stuff. So there's 2 ways to solve this equation. One is to just do simultaneous equations, so rearrange say this equation and then substitute it into the other one. The other way to do it is to use the matrix method with Cramer's rule. And that's the one that I'm going to use, but I think they're probably equally time-consuming in their difficulty. So let's just double check what transfer function we're actually looking for. So we want theta 2 divided by t. So that's what we're going to go for. So we'll start by setting it up in our matrix method. So matrix A is the one of all of the constants in front of the unknowns. X is the unknowns, so in our case theta 1 and theta 2. And B is the matrix of values on the other side of the equation. So we have t and we have 0. So this is just a standard maths thing, not specific to control at all. Alright, so our A matrix is going to start with J1s squared plus a D1s plus K. Well, what's in front of theta 1? Theta 2, it's just going to be negative K. Maybe it'll leave me a bit more space. There we go. Alright, so our two unknowns was theta 1 and theta 2. And on the other side, it's equal to the constant, so t. So we can go through and fill it out for our second equation now. So for theta 1, we have negative K. And for theta 2, we have this. And we've already filled in our two unknowns, and we have 0 on the other side. So just to quickly point out how we can kind of double check at this stage that we've picked up all the terms that we wanted to. So I'll just copy down the thing that we had before, the original question. So what we're going to see is that on the diagonal, just like with the spring mass damper systems, we end up with positive values. So what that relates to is if we take this first one, for example, this was the one that was related to J1 inside our free body diagram. And what you'll notice is that you pick up the positive of everything attached to that part of the shaft. So you've got the actual inertia itself, which is this J1s squared, but you also pick up it was attached directly to a damper, so that appears, and it was attached directly to the spring, so that appears. For the second inertia, that related to this line of the equation, and you can see in this bottom corner one, we've ended up picking up the inertia term for that mass, we've picked up the damper that it was directly attached to, and we picked up the spring that it was directly attached to. And finally, on these diagonals, what we're going to find is that we end up with the negative of what's in between the two different parts of the shaft. So between J1 and J2, we've only got a spring, and it's ended up being a negative in there. So that's how you can go ahead and double check that you've picked up everything in your system, and that also you've got the correct signs on everything in your system. So I've just quickly noted down the pattern here. So you can see that on the diagonals, we've got everything that's attached to our various different inertias. And then on the other sides, reflected across the diagonal, we have the negative of what's in between those components. Theta 1 and theta 2 are the angles, and on the right-hand side, we're going to pick up any external torques applied to our system. So we had an external torque applied to J1, so that's why the T appeared. We had no external torques on this one, so that's why this ended up being 0. So that's basically the pattern, so you can double check that you've got everything that you need within your equation. Okay, so getting back to solving this, what we want to get out is theta 2 divided by t. So using Cramer's rule, we can get that from our matrix. So we're going to solve for theta 2, since that's what we want inside our equation. And what we need to develop is our two determinants. So on the top line of our equation, we're going to have 1, and on the bottom line, we have another 1. So since we're looking for theta 2, which is the second variable, this is the first one, this is the second one, we need to slot this matrix into the second column of our A matrix. So that's the first column, that's the second column. If we were wanting to solve for theta 1, we would take this and put it in the first column of our A matrix. So let's go ahead and fill this in. So since we're looking for the second one, the first column stays the same, and the second one has been replaced with t and 0. And now for the bottom line's determinant, we just copy straight down this A matrix. Okay, so now we just need to go and solve for these determinants. So for the top one, it's going to be this times this, which is 0, minus this times this, which is tk. And for the bottom line, we've got this times this, minus this times this, so it's like negative k squared. Alright, keeping on going. So the transfer function we were looking for was theta 2 on t, and we can get that just by dividing down to the bottom line. So k stays up the top, and I'm going to make the effort to expand this out, because what you should see with these 2 degree of freedom systems, which are purely rotational, is that whatever ended up in this minus part on the end from the determinant should cancel with something else inside the equation. So let me take the effort to expand out all these brackets. Okay, I might continue this on the next line. So all of that is from these two brackets, and then this one's going to become negative k squared is k squared, and we've got another negative in there. So what we can see is that that k squared is going to cancel with that k squared, and we can conclude our final answer by grouping together all the different powers of s. It's not 100% necessary, but it will make it easier when you have to go on and use this transfer function in other things. So for the s to the fourths, we only have that. For the s to the cubes, we end up with this one and this one. For the s squareds, we end up with a couple. We've got 1, 2, 3. And we've got a couple of s terms as well on the end. Cool. So this becomes our final answer for the transfer function. And it's even in a nice form to be able to keep working with it. So that's all there is for this question, and I'll see you in a different video.